Hi everybody, in this exercise we are going to study operation of HVdc converters in different control modes using the given models. At the beginning, let's open the files. We can look into the parameter file to see the given variables. This also always helps to understand the model in a better way. So here we can see which variables are given. We don't need to run it because it will be run from the model properties in this Simulink model, as we saw in the previous modules also. Now, after opening the Simulink file, we need to check that the setting of each component is as it is given in the exercise document. The first thing is the control mode of the HVdc converter. So we can see it's a Vdc-Q controller, which means it is controlling DC link voltage and the reactive power on the AC side. You can look into the model to see how it is built. So this is the overall picture of the HVdc converter model. You can see there is a converter filter at top and there are the control blocks at the bottom. Let's zoom in to have a closer look at the model. So here we have this VSC converter, which is modeled as the average base model. Then we have a filter, RLC filter of the converter. Finally, we have this three-phase output ports. At the bottom of this model, we have a Vdc-Q controller activated. Inside the controller, there are three control blocks similar to the one that we developed at module 2 when developing the Winter 1 controller. You can see there is this ABC to DQ and also DQ to ABC transformer and the controller in the middle. By going inside each block, we can see how each block is implemented. Inside the DQ PI controller, we have VDC controller. If we go back, we can see the outer controllers, which is a Q or VDC controller. Inside the Q controller or Q or voltage controller is this PI controller again, similar to VDC controller. The PQ controller is similar to Vdc-Q controller, except that in the outer loop we control active power instead of reactive power. The rest of the controller is similar to Vdc-Q controller. So we checked the control mode of HVdc converter and also we had a look into this model. After that, we need to make sure that the references are giving the values which is mentioned in the exercise document. For VDC reference, it is stepwise. So there is a step, P is 0 and also Q is 0. If you go inside, we can see how it is implemented. It is simply a switch which is changing between, for example, 0 and these values, depending on the mode that we select on the dialog box of each block. So everything looks fine, and in the next step we need to run the simulation and look into the result. If we look at the workspace, we can see that the parameter values are available in workspace because of the initialization from Simulink. I encourage you to look into the model properties of Simulink model to double check it. Now let's run the model. So it runs. We can open the scopes now to see the result. We observe a step in the DC voltage. If we zoom in, we can see the transient response of DC voltage controller and also other signals which are P and Q. If you want to know why it's behaving like that, we can go inside the reference and see that at t equal to 10 seconds, we have this step from 1 to 0.9. And since the converter is in VDC control mode, it is following the reference of VDC and changing and controlling the DC link voltage to 0.9. But active and reactive power are 0. For reactive power, it's easy because the reference of reactive power is 0. But for reactive power, if we go inside the model, we can see the reference of reactive power is not actually connected to this Vdc-Q control block. And the converter is controlling VDC of the DC link. So the converter is trying to control the DC link voltage by balancing the power at this DC link. Knowing that converter is the only component connected to this capacitor and there is no other power injection or current injection to the DC link, we can conclude that for balancing the voltage at DC link, converter needs to make it control the active power to 0 during a steady state. But there is this step in the DC link voltage which introduced transient in active and reactive power. We can see that the transient behavior it's noticeable for active power. And that is because the converter is controlling the DC link voltage and this, bringing it to the new set points by injecting or extracting active power from capacitor. A step down in the DC link voltage means that we are extracting some power from the DC link and subsequently we are injecting it to the AC grid. Now if we look into the power, we can see that during this transient it is the power is positive. So positive power means that we are extracting power from DC link and injecting it to AC side of the converter. In this way also you can foresee the transient behavior of active power if it was a step up in the DC link voltage. So in the next step we need to set their QREF mode to stepwise and the DC mode to 1 per unit, so no step in the DC link voltage, and run the simulation. In this case, we expect that reactive power at AC side is following the reference or set point of reactive power because the control mode is set to Vdc-Q and Q is set to the stepwise. So here we can see that the measured reactive power is following the set points, and the set point is like a stepwise defined using the values that we can see here. But the DC link voltage is constant because we set it to 1 per unit and there is no step here. There are some small impact from reactive power steps on DC link which are negligible. So we discussed this part and we could see that the converter is generating the set point of reactive power and while keeping the DC link voltage at 1 per unit. In the next part, we are asked to look into the reactive power behavior and its relation with the leading or lagging of the current respect to the measured voltage. Here we can see that the current is 0 at the beginning because the reactive power is 0 and also active power is 0. And also after at the final part it is 0, but in the middle we can see some currents are flowing because of the reactive power. To understand the relation between the reactive power and current, let's consider the segments. For example, at t equal to 5 seconds, the power we can see at this time it is 0.2 and it's positive reactive power, the measured value. At this instant, we can zoom in to look into the behavior of the current respect to the voltage. We can compare them like this with three phase, but probably it's easier to just focus on one phase. Let's disable phase B and C and just keep phase A. Here, based on this, we can see that current is lagging voltage by 90 degree, and it is 90 degree because there is no active power injection in this case, and all of it is reactive. The main thing is that we understand that when the reactive power is positive, the current is lagging the voltage by 90 degree. Also, we can consider it for other segments. For example, at t equal to 7 seconds. In this case, we expected to see the same behavior, except that the amplitude of current is different because the value of power, reactive power, is different. But concerning the lagging or leading, it's still lagging because the sign of reactive power is same. For the next segment, it will be same. So let's go to the last part, which has a negative reactive power. In this case, we expect to see an opposite behavior, which means that the current will lead the voltage by 90 degree again, because still there is no active power flowing in the system. And by looking into the waveform, we can confirm that the current is leading the voltage. But the other important thing is that what is this current, or how is it measured? That is very important to understand this lagging and leading. So let's see which current is that by following the signals. We can see it is in this bus 1, and the current is measured from the port which are labeled with capital letters toward the port which are labeled with small letters. If we go back, we can see that these capital letters are on the converter side, and the small letters are on the grid side, which means we are measuring the current which is flowing from converter to grid. So based on all this observation, we can state that the positive reactive power happens when the current which is flowing from converter to grid is lagging the voltage by 90 degree, or if there is a active power, simply is lagging the voltage. So at this point, we have built this model, which consists of a capacitor with a converter and connected to the grid. And as we saw, it is able to follow the set points of reactive power. Probably you have recognized this is a very famous component in the power system, which is actually a STATCOM, and STATCOM is able to provide reactive power simply by a capacitor and a converter. In the next step, we will introduce active power injection in DC link and see the impact on the result. We are asked to uncomment the current source and connect it to DC terminal, and also run the simulation again. So let's do that. Uncomment it, and you can look into the dialog box of current source. It is just initialization because it's controlled externally. For controlling this current source, we have this step signal which goes from 0 to 0.2 at t equal to 3 seconds. And using this gain, we make sure that this 0.2 is equivalent to 0.2 per unit of active power. So we expect to see 0.2 per unit active power in the output of converter if we neglect the losses. After running the model, we are asked to open the PQ Vdc plots and interpret the result. Definitely, we expect that the active power has a non-zero value in this case, and we can see that it really behaves like that. And Also, the value of the power, you can see it's 0.2 per unit, as we discussed earlier. And also the active power is not following the reference set points, which was 0, because we haven't changed the control mode of converter, and it is still controlling VDC. In this case, if we want to explain why the active power is not 0, we need to consider that the converter is still trying to control the DC link voltage to the set point, which is 1 per unit. But this current source is injecting some active current to the DC link. So the converter will extract this additional power from DC link and send it to the AC grid. So we expect to see this power which is injected to the DC link to appear on the AC side, and since it is from DC link to AC side, the sign of the power will be positive based on the discussion that we had on the active power sign convention. In case you want to know where these powers are measured, you can follow the signals. So go inside the converter model and PQ measurement, then you can see that it is obtained based on the measured voltage and current at the filter bus of the converter, and that is where we measure and plot the active and reactive power. For the reactive power, it is following the set points still, because it is Vdc-Q and is able to control the reactive power to the set points. Also, we can observe this overshoot in the DC link voltage, which is normal, and that is how actually the controller is reacting to the change in the active power. Otherwise, if there was no change in the DC link voltage, the controller would not detect anything and wouldn't react. But why we see it as an overshoot and not a voltage drop, that we can discuss. If you look at the model, we can see that this current source is injecting the current or power to the DC link, and then the converter will try to extract this additional power from DC side and transfer it to AC grid. But there is a delay in the reaction of the DC link voltage controller. So at the beginning, when the current source injects power to the DC link, there will be a surplus of power before the controller reacts and brings back the voltage to the set point. In the next step, we are asked to change the sign of the current source and also run the model and observe the result. Here, by changing the sign of this final value, we are actually changing the direction of the current flowing on the DC link. So in this case, we are extracting some power from DC link. In this case, we can expect that the power flow is actually from AC side to DC side, and at the beginning, during transient, the DC link experience a voltage drop because the power is being extracted from the DC link. So here you can see that the active power is minus 0.2 because the direction of power is changing, and also we see this voltage drop in the DC link during the transient. Here we can compare the impact of the active and reactive power on the DC link, and you can see that the impact of reactive power is negligible compared to what we see for active power. For example, the first step of both active and reactive power is 0.2, but the impact on DC link voltage is much higher for active power. At this point, we have built this converter model, which is connected to a current source on the DC link. In this case, we can control the flow of the active power by giving the appropriate set points to the current controller. But what if we want to control the active power by the converter itself? So is it possible to change the control mode of the converter to PQ instead of VDC? which is the next task in this exercise. So let's comment out the current source and also change the control mode of converter to PQ controller. If we go inside the model, we can see that the PQ controller is activated in this case. And also let's change the set point of the reference values and run the model. Here we expect that the converter is taking the reference value of active and reactive power and tries to control the power to the set points. But if we look at the resultant signals, we can see that the DC link voltage is not controlled anymore. So also it looks that the active power is controlled to the set point, but the problem is that the DC link voltage is not controlled actually, and the model is not working properly. The problem is that there is nobody taking care of the DC link voltage. If you want to explain this behavior, we can say that the voltage of the DC link is out of control and it is increasing or decreasing depending on the active power injected to DC link. So if you want to solve this problem, we need to somehow fix the voltage, DC link voltage. So the DC link voltage is controlled somehow or is fixed, and the converter will be able to take care of the active and reactive power, which is actually the next task in this exercise. You can see that in this exercise we are building step by step the HVdc converter model. At the beginning, we started from the StatCom, which was a capacitor with converter. Then we introduced this current source, and now we want to control the active power by the converter. And for that, we need to fix the voltage. One way for fixing or having a constant voltage is the DC link voltage source. Let's give the value of the voltage equal to the nominal value of DC link. So we know it is 1 per unit. Now if we run the model, we expect that it's behaving properly because the DC link voltage is fixed and the converter will control the active and reactive power to the set points. After running the model, if we look into the scopes, we can see that the DC link voltage is fixed because it's a DC link voltage source, and the active power is controlled to the set points. So in this case, the converter is able to control the active power in addition to the reactive power because the DC link voltage is fixed or is controlled by another component. But is this really a practical solution? Probably not, because that means we need a huge battery storage which is able to provide the active power we need, or also to absorb the surplus active power. A practical solution is to use another converter for controlling the DC link voltage, so we can control the active power by this converter, which introduce us to point-to-point VSC HVdc transmission system, which is an example for that. I encourage that you make this layout by yourself and test it. So in this case, you need to make one of the converters in Vdc-Q control mode, and the other one is able to operate in PQ control mode. Note that the active power flow in this system will be linked by these two converters, which one of them is controlling DC link voltage and transferring the power from one side to the other side to control the DC link voltage, and the other one is actually controlling the active power to the set points. But for reactive power, these two converters are decoupled and they can control the reactive power on the AC side of themselves individually without any impact from the other component. I encourage you to build this model and also test it for different operating point and set points and see how is it working. And this is the end of exercise for module 8.